In this slide, we will talk about the error estimate for the golden search method. And for this, let's remember the movement of the golden search. If x2 was the mean optimum function, then we will just remove xu, meaning that it will be in the lower interval, xl, x2, and x1. If x1 is optimum function, then we will remove a lower bound, xl. That means we will have the result in the upper interval x2, x1, and x2. The reason of removing, for example, here for x2, we remove upper bound because we calculate x2 with upper bound. You can think that way. You can have a connection. X2 was calculated from the upper bound. That's why we remove the upper bound and have the other three. In here as well, we calculate x1 from the lower bound. That's why we remove the lower bound, and we use the remaining three. And here the interior points are symmetrical because we have a golden ratio. So either case can be used to define the error. So any of these can be used to define an error. Let's check this with the upper interval. If the true value were at the far left, the maximum distance from the estimate would be calculated as delta xa x1 minus x2. And here actually we know that the x1 is simply calculated as xl plus r is the golden ratio xu minus xl. And also we have x2, which is calculated as xu minus r xu minus xl. So these are the formulations. We can simply write these. This is x1 and this is x2. When we organize these, we will have xl minus xu and plus 2 times r xu minus xl. And from here 2r minus 1 xu minus xl. Or r is the golden ratio, that's why this is actually 0.236 xu minus xl. Similarly, if the true value were at the far right, the maximum distance from the estimate would be, from here maybe we can calculate, then delta xb equals xu minus x1. In this scenario, we will have xu already, and for x1, we will have xl plus r xu minus xl, and this becomes 1 minus r xu minus xl, and this is equivalent to 0.382 xu minus xl. So this case would represent the maximum error, and this result can then be normalized to the optimal value for the iteration, and the optimal value can be defined as xopt, and we can have an approximated error. The error approximation is 1 minus r times xu minus xl divided by normalization with xopt times 100%. So this can be used as a basis for terminating the iterations. Use to check convergence and terminate the iterations. In this slide, we will show the algorithm for the golden section search. And from the example, you actually captured the algorithm iteratively, so we can use that as in a pseudocode, as you can see here. Basically, we will have the initial low and high values, lower and upper bound, in other words. We will have a limit for the error and function and the maximum iterations. And R is the golden ratio, you can see the value. Lower and upper values are defined as these. Now in the first iteration we calculate D as the golden ratio times the difference of these. And x1 is this formulation and x2 is this formulation. And then we calculate the function values of them. And we make a comparison. If f1 is smaller than f2, then we get x1 as the optimum. Then the lower bound will be x1. Otherwise, we will have f2 smaller than f1. Then we will get x2 as the optimization point. And in that case, we will have fx as f2. So this, we already did this in the example as well. And after this, we will have the d again and calculate xu and minus xl as the interpolated point. And in here, if f1 is smaller than f2, we will have lower bound as x2 because f1 was our minimum. And x2 is x1. We always do this, change the parameter value. And x1 is with the summation of xl plus d and the function values. Otherwise, that means f2 smaller than f1, then xu becomes x1, and x1 is x2, and x2 is calculated from the new upper bound and function values. And we finish this. So, and we increase the iteration. And we continue. If f1 is smaller than f2, then again the optimized points is x1. Otherwise, it's x2. And if the optimized point is not 0, then we calculate the error value that we gave the result. In the previous slide, we showed this formulation. You can simply write it here. And if this approximation value is smaller than the predefined value, then we stop, or the maximum iteration is reached, we stop here, and we obtain the optimum point. This is basically a good algorithm to be able to complete the golden search method in a, for example, MATLAB program. So the x value for the optimum is returned as the function value Ch08, and in addition, the value of fx at the optimum is returned as the variable fx. So these are used as in the algorithm, let's say, and we can simply implement the golden search method using this algorithm. In this slide, we will see the importance of reduced function evaluations, because the golden section search actually has reduced function evaluations. This means that we are using some function values calculated in a previous iteration in the next iteration as the existing function value. So this means reduced function evaluation. We don't need to recalculate them in the next iteration. This is important in two contexts. The first one is many evaluations. So in some cases, as you can see here, the golden section search may be a part of much larger calculation. Then the golden section search algorithm may be called many times, and therefore keeping function evaluations to a minimum could play a great importance, and it can pay the great dividends for the optimization process. Also, the time-consuming evaluation is another case. For pedagogical reasons, we use simple functions in most of our examples here to teach you in a clear way. But in reality, a function can be very complex and time-consuming to evaluate. It can be a big program that you need to solve, and it can take so much time. For example, optimization can be used to estimate the parameters of a model consisting of a system of differential equations. For such cases, the function involves time-consuming model integration, and any method that minimizes such evaluations would be advantageous. So instead of having this golden search, then we can use other methods to be able to have maybe a reduce function as well. But in the golden search, again, we will have reduce function evaluations because, as I said, in the next iteration, for instance, instead of 4 values that we guessed initially, we obtain the function values of them. In the next iteration, we are not calculating 4 values. Lower and upper bound are already there. One of the x1 or x2 is already there too. We only calculate only one function at each iteration. So it is a reduced function evaluation actually for the golden section search.